All right, so we are going to look at solving exponential and logarithmic equations in this section. We're going to look at 3 different methods for solving exponential equations. Problems where you can equate the base, problems where you can't equate the base, and also problems where the variable is only in one exponent. And then for logarithmic equations, those are actually going to be easier. We're going to look at how to solve when every term has a log and when every term doesn't have a log. All right, so let's take a look. So first, let's just remind ourselves, what is an exponential equation? And when we're solving exponential equations, the important part to remember is the variable is in the exponent. Just because the problem has an exponent doesn't mean it's exponential. I mean, think about quadratic equations. Quadratic equations have exponents, but the variable isn't in there. So we're talking when the variable is in the exponent, as you can see in these examples. Okay, so equating the bases is actually really easy as long as you can spot that you can equate the bases. So if we take a look at the first one, or on one side the base is a 5, the other one is a 25, but we can rewrite 25 in base 5. So that's what we're going to do. We're going to make that 25 into 5 squared, but everything else in the problem staying the same. And then, don't forget with your properties of exponents, when you have a power raised to a power, you can multiply the exponents. And now that the bases are equal, the exponents have to be equal. So we can just equate the exponents. And then the problem turns into an easy one to solve. We distribute the 2. Let's get the x's on one side, the constants on another, so we can see x is negative 3/4. So that's the basic idea. I have another example over here. If we take a look at this one, okay, so this one's a little tougher. We have 1/8 and 4. So the thing to spot is, let's focus on just the 8, because we know negative exponents can make fractions. If we look at just the 8 and the 4, then hopefully it's starting to become a little more obvious. Still not totally obvious, but they can be written with a base 2. So that's what we're going to do. 1/8 is 2 to the negative 3rd. And 4, that one's easy, that's 2 squared. We multiply our exponents. And now we can see 2 to the power of something equals 2 to the power of something. Oh, there's some things have to be equal. And so we can equate the exponents. And then again, it's easy. If we distribute the negative 3, distribute the 2. Let's see, we have 19x. Oh, what am I doing? We have 13x equals negative 11, so x is negative 11/13. And there we go. So that's the idea of equating the bases. So now let's look at a couple for you to try. Okay, so give these a shot, and we'll take a look together. So go ahead and pause the video, but then we'll look at the solutions together. Okay, so here are the solutions. So the key with the first one is they could be written as base 6. Square root of 6 is 6 to the 1/2. 36 is 6 squared. But then we do the same exact process we did before. Second example, a little trickier, but if we look at the numerators, 16 and 8, those are powers of 2. 81 and 27 are powers of 3. That can help you see the 2/3. One little note here, when you're writing it, make sure that you put, like when we want to put the 4 on the 2/3, it's got to be written with parentheses. If I write 2/3 to the power of 4, we can clearly see the 4 applies to the entire fraction. But if you just do this, it actually looks like the 4 is only on the numerator. In fact, that's what that means. Mathematically, that would mean only the 4 on the numerator. So make sure that you do put parentheses around the entire fraction. Right. If you have questions, you can pause the video and take a look. I think you'll be able to figure it out, but that's the idea behind these. Okay, so let's look at what happens when you can't equate the bases. Okay, so let's look at this problem. When you can't equate the bases, it's a little trickier. So we're going to use logs. So in this case, we have to use logs to help us get the exponents out of the, or the variable out of the exponent. Now, we want to put our answer in what's called calculator ready form, meaning it'll be ready to type into a calculator, but we don't want to actually pick up the calculator until the very last step. So I'm going to start by using, even though we have base 5 and a base 7 in this problem, I'm actually going to use a log without a base 5 or base 7, because neither one of these is a calculator ready base. You got to use base 10 or base E. I'm going to go ahead and use base E just because it's easier to write natural log, but it doesn't matter, the same exact process. So we're going to take the natural log of both sides. And now we can use our properties of logs to get that exponent, or the exponent out in front of the log. So we're using that power property of logs. I'm going to do that on both sides. So remember, when the power is on the entire argument, you can move the power out in front. And now it's like we've seen before. We just have a natural log in this problem, but we've seen how to do these before. We're just going to distribute the natural log on both sides, collect all the terms with an x on one side, factor it out, and so on. So you'll see it. We're going to distribute the natural log of 5. And then over here we distribute the natural log of 7. And then I'm going to collect the terms with an x on one side. So we have x natural log 5 minus 2x natural log of 7. And on the other side, I'm going to put all the terms without an x. And then we can factor out the x on the left-hand side. That gets it in one place. And finally, we can divide. And there's our answer. Now there's different ways we can write our answer. So I'm going to go up here. So one way is this. I'm just going to copy it down. Another way is we can use our properties of logs to condense that answer down a little bit and simplify it. So remember our power property. We can move this 5 out onto the 7 and make it 7 to the power of 5. We also have subtraction between two logs with the same base, so we can condense them using division. And we can do something very similar to the bottom. So it's going to be natural log of 7 to the 5th over 5 over the natural log of 5 over 7 squared. Which one's right? You tell me. It actually, it's kind of a toss-up. Honestly, if it's a free response question, you can put your answer either form. If it's multiple choice, just take a look at the answer choices. They'll let you know. Well, that didn't really work out well. So look at the answer choices. They won't have both as an option, unless it's one of those kind of problems where you can choose more than one answer. But just take a look at the answers and you'll be able to see, did they condense it or did they not condense it? Now, the other thing is we could type this in a calculator. And when you type it in on a calculator, you're going to get an approximation of about negative 3.558. Now, I want to point out something here. A lot of people think, oh yeah, the calculator, it's actually telling me negative 3.557735498. Wow, that's really precise. That must be an exact answer, but it's not. This is an approximation. This decimal keeps going on. So this is only an approximation. I don't care how many digits after the decimal point you give me. It's still an approximation. These are exact answers. Pay attention to the directions. And I'll tell you right now, I'm always going to want your answer. This is what I mean by calculator ready form. This is what you type in on the calculator. Notice I didn't pick up the calculator until the very end. So I never put like decimal. I never found the natural log of 7 and got a decimal answer there and a natural log. No. I waited till the very end. Then I typed this whole thing into the calculator. That's going to give you the most precise answer. And I say most precise. If you need it in a decimal form, if you're actually going to use this in application, this is the most precise decimal approximation when you wait until the very end. But these are the exact answers. So always, always, always give me the calculator ready form first, and then you can type in the calculator if you need to give an approximation. Okay, let's try one now. So this is one for you to try on your own. Go ahead and pause the video and try it, and then I'll reveal the answer. All right, so here we go. So same exact idea as what we did before. We cannot equate these bases, so we put the natural log in front of both sides, or common log. You could use log base 10. And then you can use power property to bring the exponents out in front. Distribute, collect the terms with the x on one side, factor out the x, divide, condense. There's your exact answer. And there's the approximation. Now I do want to point out one thing, and this, I think this is a better practice in general, but this isn't required. Notice when I went from this step to, it was this step to this step, when I was collecting the x's on one side. I went for the x's on the right-hand side. I mean, normally we put the x's on the left. Why would I do that? Well, I actually wanted to minimize the negatives, which, like I said, in general is a good practice. I could see, like, if I put the x's on the left, that term's already negative. This term coming over would become negative. This term would have to go over to that side and also become negative. Too many negatives. So I just chose to collect the x's here. That way it's a nicer looking answer. So it's in general a better practice. All right, so that's what happens when you can't equate the bases. Okay, so now we're going to look at the third one. What if the variable is only in one exponent? So let's look at this. So I have a really basic one here, and I do want to point out something here. So you may go, okay, well that's easy. I mean, duh, you just rewrite it, do the around the world thing. So it's log base 7 of 10 is x. Ta-da! Except, remember, I wanted the answer in a calculator ready base. So if you do it this way, you got to use a change of base formula, which on this problem isn't bad at all. Again, you could use natural logs or common logs. I see a 10 there. Instead of using natural logs, which is my norm, I'm going to use common logs. Because if I do common logs, this would be log base 10 of 10 over log base 10 of 7. And we know log base 10 of 10 is just 1. You get a nicer answer there. It wouldn't be wrong to use a natural log of 7. It wouldn't be wrong to use natural log when you use change of base. But in this case, just a little nicer. So yeah, this is totally legitimate. But you can also start off with taking the, I'm just going to rewrite it here. Just like we were doing up above on the previous problems, just start with a calculator ready base. Now, since I used common logs on that first method, I'm going to use common logs here. So we'd have log of 7 to the x equals log of 10. Now I can move the x out in front. And we know log of 10 is 1. And when I divide, oh, look at that. I get the same exact thing. 1 over log of 7. So I will say this. In general, you can do it either way. You can start off with whatever base was given and use change of base to change your answer. Or, excuse me, you can start with a calculator ready base. I will tell you in general, I like to start off with a calculator ready base. This problem was very simple and I wanted to show it to you as an example, but when they start getting more complicated, it actually becomes easier rather than waiting till the end. What happens when you wait till the end to use change of base formula, you could run into complex fractions. Because, you know, when you use change of base formula, you're creating a fraction. Depending on what your answer looks like, you might create a fraction within a fraction that you have to simplify. And so I like to just avoid that altogether. I start off with a calculator ready base right from the beginning. Never run into complex fractions. So that's just my recommendation. Okay, so let's see. Let's take a look at this one. So we're going to do this one together too. So in general, now it's a little more complicated. There's a little more going on in the problem, but we still have a variable in the exponent. So what we're going to do is you always want to isolate the exponential part first. That means get the base and exponent by itself. We have to get rid of the 3 and the -1. So we're going to do what we normally do. We're going to add 1 to both sides. And then we'll divide it by 3. And then in this case, since I have a base e, I'm going to use the natural log. Take the natural log of both sides. But we know here when we have log base e of e to something, since the bases match, they'll cancel out. We have 2x equals the natural log of 2. So x is the natural log of 2 over 2. And there is our exact answer. I just want to make a note here. This one's kind of sneaky. Remember, natural log of 2 over 2 is the same thing as 1/2 natural log of 2, which means you could write it as natural log of square root of 2. I don't care which way you write it. Any one of these three is fine. But again, I just wanted to point that out in case it's a multiple choice test. And maybe this one isn't given, but it's given in this form. So just remember that they are equivalent. All right, so that was that. Now here's one for you to try. So give this one a go and see how that one goes. Go ahead and pause the video, try it out your own. All right, so here was this problem. Now I will say this, just a tiny little thing. Technically, we do have a complex fraction, only because anytime you have a decimal inside a fraction, decimals are really fractions. So now we have a fraction and a fraction. That's why I divided here. We have another decimal in a fraction. But this one's easy to take care of. If we do, if we think of that 1.5 as 3/2, then we can just take the reciprocal. 1 over 3/2 is 2/3. So a slightly better way to write this would be 2 natural log 1.825 over 3 natural log 5. That looks a little better. But I'll leave that one up to you. All right, so that's exponential equations. Let's look at logarithmic equations now. Okay, so first of all, just really quickly, just like exponential equations had the variable in the exponent, logarithmic equations have the variable in the log. Okay, so what if every term has a log? Here's a really basic one. Again, we're going to start off basic and we'll get a little more complicated. But if we look at this one, this term has a log, that term has a log, every term has a log. In fact, in this case, we only have one log on each side. So if log base 8 of something equals log base 8 of something, these somethings have to be equal. You can basically just equate the arguments. So 6x minus 11 equals x minus 1. Let's see here, subtract x from both sides and add 11. Why is this so hard? X is 2. There we go. Now, there is one little special thing with logarithmic equations that you must do. You must check for extraneous solutions. This is another one of those cases. Now the good news is it's an easy check. What you have to do is make sure your argument is positive. You can't have a negative in the argument. So if x is 2, well, 6 times 2 is minus 11, that's positive. 2 minus 1, that's positive. Okay, it's a keeper. We're done. But you always got to check, because you never know. So that's the basic idea. Let's take a look at one that's just a little more complicated. So this one's not too bad, but again, every term has a log. We want to get it as easy as this one was. I mean, this one was so easy because we had a log on both sides with the same base. Well, remember, we have properties of logs that can condense this. This side's already down to a single log. Let's use our properties of logs to condense this side. So it's going to look like natural log of x plus 5 equals, we're going to use the quotient property here because of the subtraction sign. And now we have natural log of something equals natural log of something. Oop, those somethings must be equal. So x plus 5 equals x minus 1 over x plus 1. And now we solve it. And to do this one, I'm going to multiply both sides by the denominator, x plus 1. So that's going to turn it into this. We will multiply out x plus 1 times x plus 5. We get x squared plus 6x plus 5 equals x minus 1. Let's make it equal 0. So subtract x and add 1. Factor it. Set each factor equal to 0. And we have our answers. X is negative 3 and x is negative 2. Except we got to check for extraneous solutions. Negative 3? Well, negative 3 plus 5, that's 2, that's good. Uh-oh, negative 3 minus 1, that's negative. I don't care what that equals. As long as it makes one argument negative, throw it away. So that's extraneous. And if x is negative 2 doesn't make this argument negative, but negative 2 makes that one negative. Oh, we got to throw that one away. Both are extraneous. So, our actual answer in this case is no solution. So always make sure that you check for extraneous solutions. All right, let's take a look at one for you to try. Okay, try this one on your own and see how you do. All right, and this is what you should have gotten. So again, condense. In this case, we're using the product property to condense. Each side now is a single log, so you can equate the arguments. This was a quadratic to solve. You get x equals 7 and negative 4, but negative 4 makes that argument negative, so we're going to throw it out. 7 is the only one that we're going to keep. Okay, we just got one more type of problem to go through, and that's logarithmic equations where not every term has a log. Okay, so let's see what happens with not every term having a log. Some of you guys probably see it already. I mean, here's, again, it was a very simple one to start with, but we do have a log on one side, but there's no log over here. But we can rewrite as an exponent. And that's what you do. So 3 to the 4th power is equal to x minus 1. And 3 to the 4th power is 81. We add 1 to both sides, and x is 82. And that's it. It's really that simple. And again, don't forget to check for extraneous solutions. I forgot to mention that, but I did. 82 minus 1 is still positive, so it's a keeper. So that's the idea. Okay, let's look at another one. Okay, so what do we do with something like this? Well, we're going to eventually get it down to as simple as it was in the beginning, that first example. And that first example was so easy because the log was by itself, so we could just rewrite it as an exponent. So that's what you're going to want to do. You're going to want to get the log by itself first and then rewrite it. So I'm going to have to subtract 2 from both sides. Get 3 log of 3d equals 3. And then I can divide both sides by 3, so get log of 3d equals 1. And now we can go ahead and rewrite it as an exponent. Remember, this is a common log. The base is not written, so it's implied that it's a 10. So 10 to the 1st power is 3d. And then we can just divide, and we get 10/3 for d. And again, if we just double check, we can see that this will not make this argument negative. It's a keeper. So that's the idea with these. So I'm actually going to end with 2 problems for you to do on your own. So let's take a look at those. Okay, so here's one. Again, pause the video, give it a shot on your own, and then we'll look at it together. Remember, your goal is you want to try to get 1 log on one side. So I'll give you a hint here. I mean, if you don't want the hint, just go ahead and pause the video right now and try it. But if you want the hint, I'm going to give it right now. So we have a log on both sides, but we also have a term without a log. Collect all the logs on one side, and then you can use your properties of logs to get it down to a single log. So that's the idea. Okay, so pause the video, try it on your own. Okay, so here's this one. Again, get the logs all on one side. That way you can use your properties of logs to condense. And in this case, since it was subtraction, I used the quotient property. Then 5 to the 1st power is equal to the argument, multiplied by the denominator, and then it became a very easy equation to solve. And again, double check. This did not make either argument 0 or negative, so it's a keeper. Okay, one more problem. Here's the last one to try on your own. Okay, so give that one a go, and we'll look at it together. All right, so here we go. Here's the last one. Very similar to the one above. Collect your logs on one side. Use the properties of logs to condense to a single log. Remember, there's an invisible base of 10. 10 to the 3rd power is equal to the argument. Multiply both sides by the denominator, and we wind up with this. But you got to check for extraneous solutions. And you go, God, I don't know how to do this one. But sure, we can totally do this one. I mean, that's almost 3,000. That's almost 1,000. This is going to be a little less than 3. Very close, but just a smidge less than 3. Once you subtract 10, it's negative. Same thing here. This would have been negative. So there is no solution. So yes, you will be expected to do some approximating in your head like that sometimes, but that's not too bad. All right, there you go. Logs and exponents in a nutshell. Have fun with your homework. Bye.